Okay, so let's try to prove some basic stuff about independent random variables. So let's talk about independence just a minute, because we did talk about it, but it wasn't really so clear. We say that x and y are independent if knowing the outcome of one doesn't tell you anything about the other. So in other words, if you know that x is equal to some number k, if you know that y is equals to some number j, that's not going to change the probability of x being k. So these two are the same. And because x equals to k and y equals to j, two things happening at the same time, we learned that to calculate products of two things happening at the same time, you have to multiply, right? So it should be x equals to k times, if you have to multiply this with x equals to j, assuming that you know x equals to k. So, sorry, this is y equals to j. Y equals to j, assuming that x is equal to k. Now, what I wrote down here is going to be true for any two random variables, even if those two things are not, the x and y are dependent, okay? But if x and y are independent, then this one, knowing that x is equal to k, is not going to affect whether the probability of y being j, so you can just delete this because it's independent. So, and these two are the same thing. See, being independent could be written like this, or it could also be written like this. Okay, so and we are actually going to use this property to show the first thing. Now, I'm going to assume that the x and y are discrete random variables, but if x and y are continuous random variables, the only thing that changes is instead of sigma, you just have integrals. Although it looks a little bit more complicated, it's essentially the same thing, right? So let me try to demonstrate this. First, if you have a discrete random variable, what is the expectation value? Well, that's sum of x equals to xi and y equals to yj, with the probability that x is xi and y is yj. So imagine that, for example, if you are flipping a coin and then throwing a die, those two things should be independent, right? And then if the x takes the value of 1 for the tail and 2 for the head, and y is simply the number that you get on the die, then this summation will be like 1 times 1 times the probability, 1 times 2 times the probability, 1 times 3 until 1 times 6, and then that's for when you have tail for the coin, and the other one will be the number on the die, and then now you have to do the heads. So 2 times 1, 2 times 2, 2 times 3, all the way until 2 times 6, and then every time you do that, you multiply with the probability. That's what's being computed here. You see, the very basic definition of an expectation value of a random variable was just think about all the possible values that x can take times the probability of x being xi. That's what it was. Okay? So I'm just applying this formula to this product random variable. That's all that's been. Okay, so if you're convinced that this is the definition of this left side, let's see how you can get to the right side. Well, now we apply that independence. So Here we're actually summing over both I and j, so it's actually a double summation, summing over I and then sum over j. But writing two sigmas just makes things look more complicated, so I'll just put ij. So sum over all possible ij's, and then you have xi, yj times p of x equals to xi times p of y equals to yi. And from here to there, that's when I use independence. The fact that x and y are independent variables allow you to make the compute the probability of two things happening at the same time as just a simple product. And then now what you can do is see, this is like if I goes from 1 and 2, which is the tails and heads, they'll be like x1 times y1, y2, y3, all these summation will be there, right? So p of x equals to x1 plus y2, p of x equals to, no, y equals to y1 plus, so I'm trying to write this explicitly, okay? So let's write down this sum explicitly to see what's going on. First, when I is 1, then you get y1 and then y2, p x equals to x1 times p of y equals to y2 plus the next one will be y3, y4, wherever it ends. It ends at some number, yn, p x equals to x1, p y equals to y1. But then plus, then x will also go up, right? The index for the x will also go. It will be x2, y1, p x equals to x2, p of y equals to y1, y2, p of x equals to x2, p of y equals to y2, plus something like that. And then this will again go further. Now my point is this. Do you see that p of x equals to x1 is a common factor here? So you can factor that out. How's that? You can do that, right? And then once you factor that out, and you can do the same here, you can factor the p of x equals to x2 out. Then if you factor p of x equals to x2 out from the second one, after factoring, look at what remains. They're exactly the same thing after you factor it out. Do you see it? Once I get rid of these, pull it outside, what's left is y1 p y1, y2 p y2 until yn p yn. Same thing here, y1 p y1, y2 p y2, yn p y2. Exactly the same after you factor it out, right? So you can factor these extra stuff, and once you factor it, then now you have the remaining ones which are exactly the same, so we can factor by this other thing. Now, I can easily write down what's left after factoring. So after factoring p of x equals to x1, what remains is summation of p of y equals to yi. Actually, we're doing yj, right? Sorry, so this should be yj. yj. Okay? Do you agree? You'll just have y and then p of y something after you factor this out. Okay? So this is the thing that's common to all of these. Therefore, I can factor that out. Now, if I factor that out, then imagine what you get here. Those are x1 p x1, x2 p x2, x3 p x3. So what you have is sum of xip x equals to xi. This will be one factor, and the other factor will be this one. Sum of yi, yj, p, y equals to yj. So that's it. That's the proof. Because what is this? This is e of x. What is this? This is e of y. Okay? All right, so that proves the first part. Now, let me prove the second thing, but I haven't defined what covariance is. So let me remind you what variance is. What is variance? Well, variance is, it measures how far each data set is from the average, right? We take this difference, and then because we want to take the average, but if you have pluses and minus, averages will just cancel out. To make everything positive, you square this, and you take the average of these quantities. That's called variance, right? And the famous formula that I've proved a while ago is that this is, if you expand it out, you end up seeing that this is equal to e of x squared minus e of x squared. So this is a convenient way of computing the variance, but this is the definition. What's variance? It measures how each data sets are away from the mean value, okay? Or how the generated random value will be away from the mean value. That's what it is, okay? But now, what is covariance? Well, covariance measures how likely two random variables behave. So what it does is, this is e of x minus e of x times y minus e of y. Okay? And you can see that this definition means that covariance of xx, if I replace y by x, you get exactly this, right? Do you agree? If y is replaced by x, it's exactly the same. So you get the variance of x. Okay? But then what does it mean? Well, it's like this. If x and y are somewhat correlated positively, so I didn't even explain what that is, but that means that there's a tendency for y to increase whenever y to be bigger than the average whenever x is bigger than the average. And whenever x is less than the average, y will be less than the average. If something like a positive correlation exists between them, then what happens to this value? It will be, it's likely that when this is positive, this is also positive, and when this is negative, this is also negative. In both cases, the product will be positive, right? So overall, the covariance will be a positive value. Okay? So when you have a positive correlation, covariance will be positive. What if it's the other case? You can think of a negative correlated case where if x is over the average, y has a tendency to be below the average. When x is below the average, y has a tendency to be above average. Right? It's just like, say, blood pressure and heart attack. Right? So number of heart attack cases will be, no, they're actually positive correlated. What's that, the opposite? I can't think of a good one. Can you think of a good one? Something that's negatively correlated. Your blood pressure versus, no.
The harder the quizzes versus the failing rate of us.
Okay. Okay. If the exam becomes harder, then your scores go down, right? Okay, good. So that's negatively correlated. So if you have such a thing, then if this is positive, this will be negative. If this is negative, that's a positive. So in both cases, the product will be negative, right? If the product is negative, in many cases, and you're taking the average, overall, you're going to get a negative value. So you see that if two random variables have the tendency to go the opposite way, then the covariance will be negative. On the other hand, what if x and y don't have any correlation? Like, just like the example when I said the throwing a coin and then throwing a die. Like whatever outcome x is, it has no effect on the y, right? In those cases, it has all the possibilities where some are positive, some are negative, so you end up canceling. And that's what we're trying to prove. That's the intuitive reason, okay? But now, here's a really easy way to prove it. See, if x and y are independent, then x minus a constant and y minus a constant would still be independent, right? Do you agree? Yeah, it's not going to do anything. So I can just apply this rule. So what is that? That's e of x minus ex. So I can just take the expectation value of this quantity times e of y minus ey. But then, if you have two things, averages can be, like if you have two things and you're taking the averages, you can take the averages of each individual things. That doesn't change, right? So you have e of x minus e of x. But then what's an average of average? Average is a single number, so if you take the average of a single number, it's just itself, right? If you just took one exam and you got 70, what's your average? It's 70, right? So this is just going to be e of x. That's what you're getting. Same thing here. It will be ey minus ey. Okay, what is this? ex minus ex.
0.
0. So done. Okay? So we see that the covariance of two independent random variables will be 0.